Mastering the foundations of ionizing radiation. Welcome to this presentation on mastering the foundation of ionizing radiation. In this session, we will explore the core principles of atomic physics and the fundamental nature of radiation to provide a solid groundwork for radiation safety practices. Identifying the ionizing radiation threshold. To begin, let us define radiation. It is energy emitted as particles or electromagnetic waves. We categorize radiation based on an energy threshold of 20 electron volt. Non-ionizing radiation like microwaves and visible lights lacks the energy to break atomic bonds. However, ionizing radiation exceeds this 20 electron volt threshold, possessing sufficient energy to split matter into charged particles called ion pairs. This ionization process is the exclusive focus of the radiation safety officer. Breaking down the atomic blueprint. Understanding radiation requires breaking down the atomic blueprint. Atoms are composed of three fundamental building blocks. Protons carry a plus one charge and reside in the nucleus. Their number determines the element's chemical identity known as the atomic number. Neutrons are also heavy particles in the nucleus but have no charge. Together with protons, they dictate the atomic mass. Electrons are extremely light, negatively charged particles that orbit the nucleus, weighing roughly 1 divided by 1840 of a single proton. Isotopes share identity but differ in mass. While elements are defined by their protons, isotopes of the same element possess the same atomic number but differ in mass because they contain different numbers of neutrons. This doesn't alter chemical properties, but it does dictate nuclear stability. For example, hydrogen has three isotopes: protium H1 and deuterium H2 are perfectly stable. However, tritium H3 contains too many neutrons, rendering it physically unstable and radioactive. Radioactivity is the nucleus seeking stability. Radioactivity is a spontaneous internal change within an unstable atom. The unstable nucleus seeks a stable state by violently ejecting nuclear fragments or bundles of energy. This emission is what we call radiation. Over time, these radioisotopes continually decay until they eventually transform into entirely different stable elements. Tracing the origins of radioisotopes. We can trace the origins of radioisotope to two main sources. There are approximately 50 known naturally occurring isotopes found in the environment, such as uranium-238 and carbon-14. Conversely, Synthetic or man-made radioisotopes are produced intentionally in nuclear accelerators or high-yield reactors. This category includes all transuranic elements atomic number greater than 92 and is crucial for medical and research applications like technetium-99m. Alpha decay presents a strict internal hazard. Alpha decay involves the emission of an alpha particle consisting of two protons and two neutrons, effectively a helium nucleus. Because of its large +2 charge and high energy, typically 1 to 5 mega electron volt, it is highly interactive but has an extremely short range. It cannot penetrate the dead layer of human skin. Therefore, alpha particle is exclusively an internal hazard, requiring protection against inhalation and ingestion. Beta decay emits fast and light particles. Beta decay emits fast light particles, specifically high speed electrons originating from the nucleus when a neutron transforms into a proton. These particles carry a -1 charge and are more penetrating than alpha particles. Effective shielding requires specialized low Z materials such as lucite to prevent the generation of secondary Bremsstrahlung radiation. Gamma radiation emits weightless, deep penetrating energy. Gamma radiation is weightless, deep penetrating energy emitted as pure electromagnetic waves called photons. Traveling at the speed of light with zero mass or charge, gamma rays are released directly from the nucleus to shed excess energy. Because they can penetrate paper, tissue, and thin metal, they pose a significant whole body external hazard and require high density shielding materials like lead, tungsten, or depleted uranium. X-rays originate outside the atomic nucleus. While X-rays are physically identical to gamma rays, both are electromagnetic waves. The crucial distinction is their origin. X-rays originate from the electron cloud outside the nucleus, not from within it. They are typically man-made by bombarding a metallic target with fast electrons in a vacuum tube and are a standard in medical treatment and radiography. Synthesizing the four primary radiation threats. This table summarizes our primary threats. Alpha is heavy, has +2 charge, originates in the nucleus, and is a strictly internal hazard. Beta has near zero mass, a minus charge, and presents both a skin and internal hazards. Gamma and X-rays both have zero mass and charge and represent deep external hazards. However, gamma originates in the nucleus while X-rays come from the electron cloud. quantifying activity with curies and becquerels. We quantify radioactive activity by measuring the exact rate of decay in disintegrations per seconds (dps). The traditional unit is the curie (Ci), historically based on 1 gram of radium 226. The modern international SI unit is the becquerels (BQ), where 1 BQ equals exactly 1 dps. The RSO conversion standard is 1 curie is equal to 3.7 into 10 to the power 10 becquerels. Half-life dictates the physics of radioactive time. Half-life is defined as the precise time required for a radioactive sample to decrease to exactly one half of its initial radioactivity. Every isotope has a specific unchangeable physical half-life, unaffected by its environment. For perspective, half the half-life of tritium is 12 years, while uranium-238's half-life is 4.5 billion years. The core equation At is equal to A0 into e to the power minus lambda t. The core equation for calculating decay is At is equal to A0 into e to the power minus lambda t, where the decay constant lambda is equal to 0.693 divided by t half. For example, if you have 1 millicurie of tritium and 6 years pass, you first find lambda, which is equal to 0.05775, and then apply the formula to find that 0.71 millicurie of activity remains. Verify Chapter 2 Exam Mastery. In summary, to master this foundation, remember the ionizing threshold is 20 electron volt. Isotopes differ only by neutrons. Alpha and beta are particles. Gamma and X-rays are waves. The baseline conversion is 1 curie is equal to 3.7 into 10 to the power 10 becquerels. Half-life determines the constant rate of exponential decay.